Right, thanks a lot for having me. So first, can everyone hear me correctly, and do you also see my screen?
Yes, we do.
Perfect. All right, so good morning, and thanks, Guillaume, for the warm-up there. So I'd be talking about Julia first, and then about Jump a bit. So this was initially a workshop meant for like a longer time, and also I designed it first for a physical workshop, so it might need to be a bit adapted. So we'll see how this works for us now. So first thing is, so these slides are online. You can find them at the URL I just posted in the chat. So mattbesançon.github.io/slides/JuliaEME1 introduction, and then the jump one will be at the second URL here. All right, so that being done, you also have the slides, well, the notebook corresponding to these slides at this repo here, which I'll also copy paste in the chat. So you have it. So this repo you can also clone, just like you learned on the previous workshop. So you have two Jupyter notebooks that you can run if you're familiar with the interface. Otherwise, you can also run them online or view them online with a small link that varies on the README there. All right. So if we're good with the logistics, we can start with the first component of this talk will be about Julia itself and presenting why you would bother with learning a new programming language, especially for scientists, and then see what features could be of interest and good things to know, let's say, in general. All right. I also see some familiar names here, so this is good to see some people I haven't seen in a long time, well, since we had conferences. So yeah, hi everyone, hi the ones I know there. All right. So first, I wanted to take a view on challenges in scientific programming in general, so programming for science. So what's the state of the art or the state of affairs, let's say? What do we need in different situations, and how do different tools cover these needs? Right, then we'll see what Julia actually is. So I'm not sure if this is really the first time you get exposed to the language or if you've already been a bit familiar with it. I know some people from the Poema network do work a lot with Julia, so you might have heard of it at least a bit. And then we'll see, so some of the tooling Julia has, especially oriented for scientists. We won't see everything, I mean, this is a general purpose programming language, so you could build web apps or anything like this, so we mostly see things from a science point of view, and especially from a, applied mathematics and engineering point of view, and some random features of interest, and then we move on to the jump part. So some parts I won't cover because we don't have the time, and some of it might not be the most interesting, but feel free to just go through the slides yourself, and you can reach out to me afterwards if you have questions. All right. So the first thing is, why would we bother with yet another programming language, especially for science? Don't we have enough? And usually scientists have two sets of needs, two categories of needs. First thing is we need some programming tools for science, and for this you usually need to be able to explore your problem set, to be able to explore your domain, to be able to quickly reproduce some results, some experiments, and so on. So you need something where you can iterate a lot between your ideas, the implementation of these ideas, and the observing the results of these ideas. So you need good plotting tools, you need quick exploration, you need to change things quickly. And then we have another set of needs that is to be able to have something that's performant and that scales well. A lot of papers and contributions wouldn't be as relevant if you're not able to solve problems of a given scale, at a given large scale, let's say. Like if you can solve an optimal power flow problem if you're in energy systems, but your method only solves them up to 5 nodes. Well, this is a toy model, but you didn't show anything new on solving actual real scale problems. So you do need some tools that are able to scale. That means you need to have some tools that you can apply to larger and larger scales if you have the corresponding computing power. So there's scaling in a general sense, and there's also scaling given that we have some hardware available that was not available 10 years ago or 20 years ago, or not as easily available. So I'm thinking, for example, of GPUs or distributed computing facilities. These days you can reasonably access GPU computers or GPU-enabled computers and servers for running some parts of your computations. And we do know that some computations now run really well on GPUs, way better than on CPUs. And so if you know that this is the case for you for some of your applications, then why should you stop? And you also know that you won't be able to reach the best possible scale if you cannot port a part of your computations on GPUs. So that's the two categories of needs I would say we have as scientists. First is interactivity and programming for science, and the second one is going fast and going on adapted hardware. Right. And the problem with that is that with these two sets of needs, we have two sets of tools arising. The first one will be what I would call exploration tools. You know them. I mean, these are Python, if you're in stats, R, otherwise MATLAB, or if you use commercial tools, SAS or Excel. So these are tools that people will open up and just quickly mess around with a problem to understand what is going on, what if I tweak this parameter, and so on. Because you can interact with your program quickly, you can change some things, add some functions, ignore some variables, or add some new ones, or replace some variables with some others, and so on. And the second set of tools will be what we call heavy computation languages. So the typical ones have always been C, C++, and Fortran. Especially if you're in science, in computational science, Fortran is a hugely dominant one in any case where you need any linear algebra done. If you're in optimization, you probably also heard of some commercial solvers, or binary solvers in general. So you don't even care which language they're written in. It's just that you have this black box solver that you call, and that's supposed to be performant for your given problem. For mixed integer linear optimization problems, Cplex, Kurobi, Skip. So I worked on now in the team partly maintaining and developing Skip here. So these would be black box binaries. So you can call them from any language, but so these are already compiled and you just use them as tools, right? And so because of this, we have these two sets of tools here, and this has technical and human consequences. First, so technical consequences because of that. You have two sets of tools, exploration and then computation tools. And because of this, you have a break in your workflow, in the sense that you would first explore your data, your problem, your parameters in some exploration first tool. You would pre-process your data to adapt it to some specific form. Then you would pass it to your heavy computation tool. And then you would post-process it again in your exploration tool and then visualize the results. So you have the first parts, so these two parts here, that will correspond to your exploration tools, and then you need to break, like to pass it to a new file, read the new file in the computation tool, run some heavy experiments, some heavy computations, and then pass it again to your post-processing and visualization part. So you're breaking twice in your workflow. And it also has human consequences that's a bit more subtle. And in large enough projects, you end up having a culture gap between the scientific part and the development part. So in academia, you could consider, for example, the people developing the tools, the computation tools, will be different from the scientists using them. And so you end up not talking the same language between the academics developing the methods and the engineers developing the tools implementing these methods, because they don't use the same set of tools. And in industry, you have the same thing with different sets of profiles. So if you work in data-intensive startups, you end up having data scientists that end up using a lot of exploration tools, and data engineers that actually do the heavy pipeline, heavy computation parts. And so these end up not talking to each other. You end up having friction because you have different departments, and you need to exchange ideas and transfer them from one to the other, and they basically don't talk the same language. Right. So what is Julia now? So Julia is a, let's say, relatively new programming language, as in it's a bit more than 10 years old now. So it's already fairly established, but in the world of programming languages, that's still fairly young. So it's dynamic. So you still get this idea of exploration first, being able to rewrite things and so on. I will dare say it's modern, even though you have to be careful with people using the term modern in programming languages or in programming in general. So I would dare say it's modern in the sense that it picks up some ideas that have been developed in the recent decades. And it's designed with technical computing or scientific programming in mind first. So it's not a specialized scientific programming language like MATLAB would be, for example, but it's designed with technical programming in mind, saying how can we make scientific programming work for everyone in a general purpose programming language. And it's compiled, it's compiled to native code, unlike some other languages, so unlike the other exploration tools we mentioned before. So it means the code you end up running is the same as, almost the same, let's say, as you would have if you had handcrafted, handwritten your C, super efficient C function. So you end up running the same thing at the end, even though you didn't write any C. Right. So this is a Jupyter notebook here. I just give you a couple of examples. At any point, so you have small numbers here, or if you have any trouble, I mean, we do have some time. I didn't pack the presentation a lot. So if you have trouble, questions, or anything, this can happen, and there's absolutely no problem. So please ask them either in the chat or unmute yourself, and we'll just get back to it and answer. Right. So I can just define some basic scalars. I don't need to declare a type first. The type will be guessed from the value itself. So if I declare x is 3 here, x here will be an integer equal to 3. I can also say y is equal to 2x. So this is if I just add a number and some scalar, it will directly deduce that this is a multiplication. I can also write 2 times x like you would in other programming languages. So x is 3, y is 2x. So this is, and the result printed is always the last value of a cell. So in that case here, this is 2x. I can also declare integers and vectors or arrays of integers. So in that case, I'm declaring an array with this square bracket syntax here, and I can add elements to it. So here I'm creating a vector of integer with 3, 4, and 5. And you see this gives me the type here, saying this is a 3-element array of int and a 1 here. So the 1 here is interesting. So this is giving you the dimension of your array. So this means in Julia, arrays are multidimensional by default, and a vector is a one-dimensional array. So this means just a bunch of numbers aligned together. Sorry for the mathematicians here. Of course, a vector is not just a bunch of numbers together, but in part, this is how you represent it here. In the same sense, if you want to think of a matrix, this will be an array of something and dimension 2 here, in the sense that it's a 2-dimensional array with rows and columns. Right. Of course, I can also define floats. So by default, this will be float 64, so a double precision number if you're thinking in terms of C or C++. And you can also define 32 floats like this with this F0 syntax at the end. I also have irrational numbers from the box. So here, for example, pi is pi is used as the real representation of pi. This is not an approximation, and when you convert it to a float, then this becomes an approximation. So here, how do I get this this syntax here? All right, did I share my? Do you see a black terminal now or not?
Yes.
Yes?
Yes, we do.
Okay, perfect. So I just opened the Julia session on the side to have some parallel. So how did I get this weird pi here? And so in Julia, if you type some LaTeX-like syntax here, like if I type pi and then I do tab, I end up with my pi here. I can do the same thing with alpha or other things. So this is fairly practical if you want to write equations or anything. So first is you have Unicode supported, like I can do alpha equals 3, and so I now have a variable called alpha. And the second thing is, so you can type them very easily with that. In fact, whenever I need some Unicode character, I usually open a Julia session and I just tab my beta and so on. All right. So yeah, irrational numbers supported from the beginning, and some specific number like the Euler constant or pi are there from a symbolic perspective, let's say.
May I ask a question? I'm Giorgio.
Sure. Yeah.
Yeah, sorry. I just tried in my computer your suggestion for pi.
Yeah.
I receive an error saying that the backslash is not a unary operator. Maybe something is missing.
Oh, yeah. So we can get back to it. So what I did is I tabbed /pi, and
Yes.
then so I didn't type enter but tab.
Ah, sorry, I missed
Yes.
it.
And then this will replace the /pi with a symbolic pi.
Thanks a lot. Yeah.
No problem.
And indeed works.
Yeah.
Sorry.
Good. All right. So we also have complex numbers from the so baked in, let's say. So you have this special constant called im, and so this is the pure imaginary unit. And so I can just add 2.0 to 3 imaginary units, and this gives me a complex number. And I can ask what's the type of this complex number, and this is a complex number over float 64. So this means, I mean, the two fields will be float 64s. I can also have complex number over integers, for example. Right. I do have also, so we do also have from the start arbitrary precision numbers. So you do know that in some cases you can get tricked with float 64 because they are not exact numbers. They do represent your real line number with some finite precision, and because of this you have some numbers that cannot be represented accurately. And so in some cases, in most cases really this is fine, and floating point numbers are really fast, so that's also why we keep them. But in some cases, you do want either to have all your computations running in super high precision, or you have some computation running and you want to validate that you have the same behavior with exact, let's say, infinite precision numbers as you have with your limited precision floating point numbers. And so for this, you have this arbitrary precision big float and big int. So you have the two. And so here I can create one with this special syntax big, quote, I put my number and I end the quotes. And this will give me exactly the same thing, up to some precision here for printing. I can also directly convert a normal number. Let's say I have my f will be 3.4, and then I can convert it to big with the same with a big function here. And so this will convert my 3.4 to a big float number. So this can end up with some rounding error. You see here, after the precision of float, you end up with something that was not there before. So that's why the preferred way to create them is from a literal, so it means a string that represents your number. And so this would be the exact 3.4 with some very tiny error at the end, but way smaller than you would have with converting a float to a big number. So you have big floats for floating point numbers, and you also have big int for large integer numbers. So given the crowd here and the interest in polynomial optimization, one very interesting thing for this is rational numbers. And so when you have rational numbers and you do rational arithmetic for, I mean, non-Tory problems, then you end up with very large numerator and denominator. And for this can be interesting to represent both of them as big integers to be sure that you won't have a problem with the size of the integers you use. All right. So we saw vectors earlier. We also have matrices. And as I said before, these are two-dimensional arrays. And so here I just created a matrix with these same square brackets. But since I have multiple lines, this would be parsed and recognized as a matrix instead of a vector. So here in that case, I'm creating this anti-symmetric matrix. No, sorry, this anti-identity matrix. And so this is telling me some basic information in the printing. So this is a 3x3 array of integers that looks like this. And then, so these are finite dimensional matrices and vectors that we created. Remember that we had this vector 3, 4, 5 that we created before. And so these are not only arrays in the sense of containers, these are really matrices and vectors in the sense that they do behave like matrices and vectors. And in that sense, you can multiply a matrix by a vector if they have appropriate shapes, and you end up with a good result. So you don't need to have special methods or functions for linear algebra. So this is built in out of the box. So matrix times vector will do the actual matrix vector multiplication. Same thing for matrix multiplication. This will just work out of the box. All right, yeah. And of course, so this matrix vector will create a new vector in the in the image of the matrix, and I can scale a vector with a scalar, like you would with vectors from vector spaces, and so you don't need to do any element-wise operation or anything. So scaling a vector just works out of the box like it's supposed to be. And of course, you can also compose matrix, linear operators together. Or matrices. So here I multiply my matrix with another matrix, and then I multiply that with my vector itself. So yeah, linear algebra will work out of the box. That's the key takeaway here. I can also create n-dimensional arrays. So in that, so not vectors, not matrices, but with arbitrary number of dimensions. And so here what I do is I first create a scalar that I create as a random number. Then I'm going to create a vector that will be a random number of 3 elements. Then I'm going to create a matrix that's going to be a random matrix with 3 by 2 elements. So when I use rand like this, this will create a random number in the a uniformly sampled random number between 0 and 1. Okay, and so this will do this independently for each of the elements of a container. So here 3 random numbers, here 3 by 2, so 6, and here I create a tensor of 3 by 2 by 5. There's a very interesting question in the chat. I presume that linear algebra is by default dense, and so we'll see how this works exactly. So the linear algebra is not dense itself. What defines the density is the containers. So here I'm creating a dense vector with 3 elements, here a dense matrix with 3 elements, and here dense tensors with 3 elements. So in that case, if I multiply them together, it will operate with dense operations, so using BLAS specifically. But if you have sparse arrays and you multiply a sparse by a sparse array, then this will operate with sparse linear algebra. So what defines the operations is the types and the function together, and we'll see how this works after. Right. So in Julia, like in many scientific libraries you have, so Python is in theory not typed. Like if you create a list of elements, if you're familiar with Python, it will just create a list and that's it. But if you use NumPy, it will create containers of a specific type, because this is absolutely necessary for any performance in scientific programming. So in Julia, when you create a vector or a matrix or any array, it will use the most specific type all the time. So here, this can be important in some cases. So here I create a vector with 3 integers here. So the type of my result will be some array of integer of dimension 1. If I add a floating point number here, it will convert everything to floating point number. So in float 64. Now, if I create a vector with first a floating point and then a complex number with integers and then an integer, it will convert everything to the most common thing. In that case, it will be a complex of float 64. All right. If I didn't have a 3 here, it would have seen a complex of integers and then an integer, and so it would have created a complex of integer. And the last one is, so I create a vector with this time 3, 4, and a string. And so a string is not a number itself. And so I don't have any common denominator for anything. And so in that case, it will not convert everything to a type. It will just create an array and say that the type inside can be anything. And so this is this type any here. And so this array of any, you can add anything to it afterwards because it just accepts anything. While if you create an array of integers, afterwards you can only add integers to it. If you want to add a floating point number, then you need to create a new array out of it. All right, so we'll get now to the central block of Julia, and I would argue that this is the central part of Julia, and this is functions first and multiple dispatch. And this will also, I hope, answer the question from Michael in the chat. So how to create a function? Well, you just have this keyword function and you finish it with an and everything in between is your function body, let's say. So this function f1 takes two arguments, x and y. If x is smaller than y, then you return the product. Otherwise, you return the division of the two. All right? Note that, I mean, as all programming languages, if you use return at some point, it stops the function. So you don't need to have an else clause here. Because if I enter here, I do return, and then I'm finished. So I don't need an else, right? And so otherwise, I will return this y over x. So yeah, this is how you would define a basic function. And I can also define equivalently, this doesn't change anything except the syntax. I can define a function in this inline form here. So f2 is defined as a function of x and y, and this is equal to an expression here. So if you just have a function that is a single expression, then this is usually a bit more practical. And this also looks a bit more like math. So I would argue that using functions for programming is way better for scientists compared to some other systems. Object-oriented programming, for instance, with classes, because as scientists, we're used to reason about functions. A function is something that takes some input, computes something, and that's it. And we are way more used to create functions and then use these functions to create other functions and so on, rather than have some object class that can read the file, but also do your computation and run your algorithms. I sometimes had the feeling that people feel bad for writing functions because they feel like it's not proper programming compared to classes. In fact, this will usually be way simpler because we are really used to function and we do reason about functions. All right, so this was the two syntaxes to create functions. Now, you can also, just like you could define Greek variables, you can also define operators. So an operator is just a Unicode symbol that you can use as a function like this, or you can also use with this syntax. And to give you first a bit of a concrete example, let me just clean this. So if you have one function that you know that is called plus, I hope you know it. And you can call it like a normal function with parentheses here. But this can get a bit awkward if you have computations, because if you want to add the result of this to another one, that will end up being like this and that. So this starts to look a bit weird, right? And so instead, there's another syntax we're super familiar with for function that's using the inline, no, not the inline version, but the in-place version, sorry. And so this is saying one argument, your function, the second argument. Usually that's how you would look at a plus operator or a times operator. And so anytime you have an operator like this, that's a single Unicode symbol, you can call it either like this or like that, with first argument, operator, second argument. And so in some cases, when you're defining some specific math-related syntax, this can be extremely practical because you can make your code look a lot more like your papers. And so in that case, what I do is I define this new operator that's using a right.arrow LaTeX-like symbol. And so I will define it as taking two arguments, A and B. And what it will do is take B at index A. So B has to be, for example, a vector. And I take the 8th element of B. And then what I do here is I apply this operator to 3 as A and this array as B. And it will return me the third element of this second argument here. So in that case, 42. So this is a very specific thing because in many languages, you have a bit of magic defined for the operators. Like operators are special cases defined by the compiler and you cannot create new ones. In the case of Julia, operators like plus, times, and so on are just generic functions. They're normal functions. So this means you can create your new operators for your specific syntax, for your specific paper, and so on. All right. One thing that Julia has been bringing, and I'll talk a bit more about it later, is it has brought some tools from software engineering to scientists also. And one of them is trying to make it as easy as possible to document your code and your packages and your programs in general. So in that case, this mechanism here is heavily inspired also by Python, who's done the same. So you have what's called a doc string, like a documentation string, that you can attach to function. So here, if I give a string before a function here, what I'm basically doing is attaching a documentation to this function. So here, what I do is I create a function called exponentiate, and it takes some parameter alpha. And what it does is something interesting. It returns another function. So here I take alpha and I return a function of x that returns itself x power alpha. This syntax exists, and so this mechanism exists in several languages, but you might not be familiar with it. So if you have questions about it, feel free to ask them. Yeah, otherwise, what I can do now is so just to show you an example, I can create some variable square that will be exponentiate of 2. And so what square has now is this function f of x with alpha equal to 2, right? And then if I call square of 3, since square is a function itself, I get 3 to the power 2, so in that case 9. All right, so that was to show you what this exponentiate function is. So imagine you create this at some point, and then somebody else uses your code and wants to see what is this exponentiate function doing. And so in that case, what you can do in Julia is use this question mark, and then you type the name, and what it will give you is, so it will try to find the best fitting name for this. So in that case, I do have exactly my name exponentiate, and it will print me the documentation for it. So, and the documentation in that case is exactly the one I added before. So given an exponent alpha returns a function that takes x and returns x power alpha. And now imagine you're not sure what the exponentiate function is called again. Is it just exponent or exponentiate? You can just question mark and add the beginning or some string that looks like it, and it will try to find the best fitting name. So it will tell you, I didn't find it exponent t, but I did find these 3, and you might be looking for any of these. Just to show you what it looks like, if I'm in the normal Julia session, for example, I want to know what so I'm going to use linear algebra, which is one of the standard packages, and I don't remember what the dot function is doing. So what I did here is I typed this question mark first, and it will switch my Julia session from the normal one to help mode. And so you see this yellow help mode here. And then I can start to type, okay, I think this was called dot. And what it will print me here is, so it will first tell me I found all these that look like dot. And then I found exactly dot, and I will give you the documentation for dot. And so now it tells me that dot of x and y computes the dot product between 2 vectors. And then if you have different versions of this function, it will give me all of them. All right, so that's it for our documentation. And so now the biggest part, I think, for this is multiple dispatch. So yeah, again, I'm going to use from the linear algebra package, I'm going to use this dot function, which computes the inner product between 2 things. So in that case, 2 vectors. And I will define a function called quadratic, and it will take some x and return the dot product between x and itself. All right, so the squared Euclidean norm of x. And now I added some special syntax here, which is column abstract vector. So this is to say that the quadratic function expects some abstract vector. It cannot take anything else. So I'm constraining the input of quadratic to be always some abstract vector. Right. And so, and a particular case of abstract vectors is the normal Julia vectors here. And so what I can do is call my quadratic function with a vector 1 and 1, and it will return the squared Euclidean norm of my vector, so the inner product of the vector with itself, which is in that case 2. All right. So that was it for my quadratic function. Now I'm going to do something interesting. I will define a new time this quadratic function, but this time I will define it with two arguments. It will take x, which will be an abstract vector, and y, which will also be an abstract vector. So I created, remember the first version was just taking one argument x. Now I define a new one which takes x and y, and now it returns a dot product between x and y instead of x with itself. And so now if I call quadratic with two arguments, it will call the appropriate function, which is in that case the second one I defined. So what's happening is I have a name quadratic, which is my function quadratic, and then I can have what is called different methods for quadratic. And so this is what it's telling me here. I have quadratic, which is a function, and it has two methods. And so this means it has two different function bodies, so two different implementations for quadratic, depending on the types and the arguments I give it. So I have a quadratic for one argument and a quadratic for two arguments. And I can do even better. I can now have quadratic that takes first some abstract matrix and second some abstract vector. And so in that case, what I will do is compute the quadratic product, so x transpose times a times x. So this will also give me a scalar at the end. And now, so the interesting thing is I already had a quadratic method that took two arguments, but the last time we defined it with a vector and a vector, and now we defined it with a vector and a matrix. And so now if I create this random matrix and I call quadratic of m with this vector, it will call the appropriate function. So the appropriate definition I have for quadratic, which is in that case this one, because it's a matrix that I give first and a vector that I give second. Now, if I call quadratic with some arguments that are not possible, for example, if I call quadratic with three arguments and I didn't define a three argument quadratic function, it will throw me a method error saying I do have a name called quadratic, it's a function, but I cannot call it with three arguments. It doesn't exist. Okay. So this part is fairly important. So if you have any question at this point, feel free to ask them. And to bounce back on the question from Michael from earlier, so the linear algebra is not dense by default. It's just that you define linear algebra functions like dot, and then they are defined on multiple methods depending on the types you have. So if you have dense arrays, then you will have a method for dense arrays. If you have sparse arrays, then you will have a method for sparse arrays. So you will always dispatch to the appropriate method depending on your types. So the advantage is you don't need to have like a quadratic dense and a quadratic sparse function. You always have the same function. Just like if you want to add numbers or if you want to add vectors, you want to always use plus, because it makes sense for you to use, well, the sign we always use for addition. If it's matrices or vectors or anything, it doesn't matter. It should always be plus. But you should still have different implementations depending on the types you give it. So yeah, do we have questions so far for multiple dispatch?
Hello, I have a question.
Yep. Mm-hmm.
So things can maybe get a little bit hairy, like for example, the operator plus, which I see has 187 methods.
Yeah.
Are there any kind of tips, tricks to manage all these multiple dispatches? Because I suppose also maintenance is an issue if you have that many methods.
Yeah. So plus, and so yeah, I will switch to my the terminal here. So yeah, as you mentioned, plus and times are the extreme examples because, well, everybody defines plus and times for many things. So you have this for complex number, real numbers, for arrays, matrices, and so on. So you're right. This can get a bit complex in some cases. What you can do is, so you have different functions that can help you. One of them is, so this at which, it's called a macro, we'll see that later, which is giving you where is the function defined if I call plus with 1 and 2, for example. So if I call this plus function with these arguments, where is located the method that is actually called. And it will tell me that the corresponding method is this one, so this definition, and this is defined in base Julia at this line. Maybe a bit too big here. Yeah. Now, and the thing you can also do is you can even type less, and it will bring you to the place in the code where this is defined. So there's another question in the chat. If I do 1 F2 1, so this is a good question. So if I do F2, so F2 would be a function that takes A and B and returns A plus B. So in that case, I cannot use it as A F2 B. The reason for this is, so the motivation for not having this is this would be too confusing if you have just a bunch of strings like this. And so the only way to have operators in the middle like this is if it's actually operators. So it means if it's a Unicode. So if you wanted to have a function defined like this, you would need like C cross. So what do I have? I'm trying to find some operators. All right, so here I added the times just like you have in LaTeX, and this is giving me oh no, I do have a method for cross. Oh yeah, this is for the cross, but it makes sense. Arrow. So I assume dotted circle. All right. So I have this dotted circle here, which is like a Unicode character. And I can define a dotted circle of A and B will be A plus B. And now for this one, I can do A dotted circle B. So I have to define A and B. So we 1, 2. Whoops. Like this. Oh, right. So this inline syntax works only for some operators, not all of them. So I should have checked before. So the dotted arrow, dot arrow definitely worked. So the one I added in the examples, but normal function names like F2 or some others will not work. So you will need the syntax with function parentheses arguments. So it does work for some operators, not all function names. Right. So in the meantime, another thing you can do is define your own types. And the key thing to take away here is if you define your own types, this will not have any performance impact compared to the native Julia types. So it means you can define your types, you can define your number types even, and they will be as efficient as the native ones. So this can be extremely practical because in some cases you will be like, yeah, but I do need performance, so I prefer using native types, which would be the case in Python, for example. You should use the baked-in functions from NumPy, and you should use the baked-in methods from the NumPy classes. In Julia, if you define your own, this will be as efficient because everything gets compiled at the end. So here, for example, I'm defining a type with this struct keyword. So this is like a struct in C or C++. So it's basically a composite type saying I have a type with different fields. And since I want people to read my code, I use this string here to document it and say this is a wrapper type for an integer. And so yeah, this is the name I give it, and it has just one field. And I use the same colon syntax to specify the type as I did for the function argument before. And then I can create my int wrapper with just passing it the value for the arguments in the good order. So in that case, I just have 1, so I pass 3 to have x affected to 3 here. And so here, if I type v.x, so I access the x field in v, so this is always accessible, and I get my 3 value. Right. The key takeaway, so multiple dispatch can still seem a bit, well, nice to have, but not necessary. but one of the key messages here is multiple dispatch allows extensions. So here I'm going to import from base the function plus. So I import it to say I want to redefine it for some cases. And so here I will define the addition between my int wrapper and an integer here. So I will define a new method for plus. Even though, so in the last case with quadratic, we defined quadratic and then we added some methods. In this case, we take an existing function plus and we add some methods to it. And so in that case, we say that if you add an int wrapper and an integer, this will give me a new int wrapper. And so now I can use my int wrapper v and add 33 directly, and it will work out of the box. So this is essential because this means you don't need to be within the compiler. You don't need to work on the Julia source code itself to change how things add or multiply together. You can, for example, create a new complex number type that you prefer, and then you can define addition, multiplication, and so on for it. Right. I won't go too much over tooling because we won't have the time otherwise. I think I'm definitely already running a bit late. Same thing for editors. So yeah, one thing I want to mention is creating packages in Julia is fairly easy or extremely easy. So you have all the tools already available. And so between the multiple dispatch and the easy package creation, the Julia ecosystem has a lot of code reuse, and this is also one trick why you don't need too many huge frameworks and packages in Julia, because you can just have very small packages do one thing, and then the other packages will use this thing somewhere else. Right. Yeah, again, so you can define arbitrary number types. So a new example here, I defined a struct called 0, and I will just say that this is a 0-like number. And so I will import, multiply, and divide and division. And I will define division between 0 and x. So this will be 0, and the same thing the other way around because I want a commutative operator. And so the multiplication with 0 is always 0. Addition of 0 and something will always be the thing. And then division will be, division of 0 by something will be 0 also. Right. And now, let's say I define so this would be, let's say, imagine a first package defining a new 0 type. And then a second package would be defining some complex algorithms. In that case, I'm just doing a bunch of additions and divisions. And now on the user side, let's say I take the complex algorithm from the package 2, I take the number type from the package 1, and I can just make them work together nicely. Even though complex algorithm doesn't know anything about the 0 type, and the 0 type doesn't know anything about complex algorithm, they just work out of the box. And because of this, so instead of using my 0 type, I can also, for example, use some real case example. So here I'm using this SimEngine package, which is for symbolic computations, and I define some symbolic variables, and I call complex algorithm with A and B. So A and B here are my symbolic variables, and what it returns is this expression here. So it returns the symbolic expression out of a complex algorithm, even though you don't need complex algorithm to be aware of using symbolic computation. It just works. And same thing if I combine a symbolic number with pi, I will end up with some expression here. Right. I won't go over automatic differentiation. If you have questions about it, there's a lot of topics, so feel free to ask them. But yeah, we won't have time. And same thing for unit-full computations. Yeah, well, why not? I mean, because of this special type thing, so we created a type called 0. You can also create types for many things, like for units. And so in that case, there's a package called unit-full that defines a bunch of units. And what you can do is unit-full computations, meaning, so this will verify that you are not adding bananas and apple. So in that case, I can add 3 joules to 1 kilogram times 1 meter per second squared, if I remember my physics correctly, and this works because I can convert everything to the same unit. What I cannot do is I cannot run my complex algorithm with 3 kilos and 2 seconds, because this will throw me a dimension error saying, hey, you are trying to add things that should not be added together. And so in that case, this will throw me an error. So this is a very nice feature to, well, if you work on physics application, then you can just basically dimension check all your computations for free by just running them with the actual units. All right, so that was it for the first part. Again, I went a bit quickly, and the first part we're just gonna hover over quick things, and then switch back to some questions. So the second part, I wanted to introduce JUMP, which is so Julia for mathematical programming. And again, you have the whole notebook for actual examples. And so the key takeaway is ideally, so we have our math that looks like it, and we would like our code to look like it too. And so what people have done is create what's called algebraic modeling languages for this. So the key examples would be GAMS or AMPLE. And so the goal of these tools is to have your math look as close as possible to your code, or the other way around. So in that case, so my math looks like it, and then my code would be something like this. I declare things, and then I will take the script and run it on the special, and pass it through the GAMS or AMPLE compiler. The tricky thing is, usually if you have a script describing your model, how do you run some algorithms on that? Because usually we don't just define model. We also want to customize the algorithms or adapt the algorithms to run on this model. And so in that case, how do you add custom sets? How do you add lazy constraints and so on? And this is usually the limit of algebraic modeling languages. And so instead, what people have been moving towards in these cases is programming interfaces, in the sense of programming against a solver directly. So here I added an example of what would it look like to define roughly the same model with Cplex. And so in that case, this is already a very different flavor. So the code is fairly complex already, and this is just adding free constraints and variables. So here you're defining specifically something for Cplex. And so you're modifying the Cplex object to create your model and then run it. So the good thing is, so this is embedded in some host language. So this means you can, for example, create a Python script that creates your model and so on. And so you can add any arbitrary algorithm loop or control flow and so on. Like if I have this thing positive, then I would add a variable, otherwise not. The problem is you get more and more distance between the model and the code you write. And because this can be hard to debug, you can also have you have two things to maintain: your model on one side and the algorithm that should correspond to the model ideally, but you have to double check all the time. Right, and a good compromise, I think, for this is what's called embedded algebraic modeling languages. So embedded in the sense that your modeling language is a library within a normal programming language or a general purpose programming language. And so the key ones are, so you have a bunch of embedded AMLs in Python, like PyOmo, Pulp, and you have JUMP in Julia, among others. So yeah, so the goal of JUMP is mostly to tackle constrained optimization, mostly. So you have extensions on polynomial optimization that Benoit, I think, will talk about at some point. And otherwise, this is mostly for structured constraint optimization, so not for black box functions or otherwise. Right. So one thing you've seen before in my code, if you're paying attention, was this at function here. So in fact, this is not a function. This is called a macro. And so a macro is a macro takes some code and can transform it. So the example I added here, if imagine you have a function that takes x, and you pass it a function that takes g. So in that case, what it will do is first Julia will evaluate g of x, and then it will pass the value to f, and the argument of f will then be evaluated itself. If you have a macro at f here, so remember this at before is giving you a macro. What it takes is it will actually take the code g of x itself. So it will not have to run g of x first. It will really get the code like you would get code in string, for example, and you can manipulate the code. So one example here is this at show macro, which takes an expression and it first prints it to the screen, and then only after it evaluates the expression. All right. Right, and I think that will be it for what I will present on that. I think we have to finish in like a couple minutes, so I won't go into many details here. but basically, yeah, show you just one example. So so I'm going to use Jump, so the library for modeling, and then I'm going to use some solvers. So Jump is a modeling library, and then you can have underlying solvers for different classes of problems. So either open source one, closed source ones for mixed integer linear programming, for linear programming, and so on. Right, so this is what a basic model would look like. So first I'm creating a model in Jump, and then I can add variables with this @variable syntax here. So, and I always give in first argument the model, which is the model I'm modifying. So here I'm creating a model and then adding a variable to it called x. Then I'm creating a second variable y, which will be bounded between 1 and pi. And then a third set of variables this time, which will be a matrix z with an index I going from 1 to 5 and an index j going from 1 to 10. And I'm going to add a last argument saying this z variable is a binary variable. So here I have a binary matrix. I can also do more crazy examples. So here I have a variable that I call delta, and this has 3 indices with one depending on I, and then the value of the bound on the variable will depend on the index itself. And I can even index with strings directly, not even with numbers. So I can say I have my variable of flower and so on. All right, I can also add some constraints. So here, my variable would be a number of pancakes, and I will create some constraint that x has to be smaller than 3y, then the number of pancakes has to be smaller than another variable, and so on. And finally, one very useful feature is at any point you can print your model, and it will print you the best looking representation of your model. So in that case, we have a lot of bound constraints. Otherwise, it will give me, so first the objective type. So in that case, I didn't set any objective, so it's telling me feasibility. Otherwise, I would have like min or max of some expression, and then subject to all my constraints. So here, my first constraint, and then these are constraints I added with some name. So if you want to specifically name some constraints, and then the expression. So this is extremely underrated and useful for debugging models. I mean, this saved the whole part of my PhD, I think. Right. So I can also create constraints, in a for loop, for example, for all my information here, I'm going to create a constraint that my number of pancake is smaller than the quantity of some ingredient times the grocery list of this ingredient, things like this. And I can lastly set some objective that's going to be, so on my model, to minimize some expression. And so the expression here is 0. So the LaTeX is a bit weird here, but otherwise 0.3 times grocery list of flour, grocery list of eggs, and grocery list of milk. Right. And finally, what I will try to do, so actually I did these mistakes when preparing the slides, so we can actually see the mistakes I made here. So the first thing is I called optimize on my model. And so so this exclamation mark here is just optional. So this is a convention in Julia, but this is not changing the function. And so here I'm calling optimize, and it's telling me no optimizer set. And this is normal because I created an empty model, so it doesn't have any solver behind it. It's just a modeling interface. So what I can do then is set the optimizer to CLP, which you might be familiar with, for solving linear optimization problems. Then I try to call optimize again, and now it's telling me unsupported constraint. And this makes sense because we're trying to set a single variable in 0, 1, which is the binary set. And CLP doesn't support that because it's just a linear optimization solver. So I need some more adapted solver. And so what I do instead is I will use CBC. So I will just reset the optimizer with CBC this time and optimize it. And now it will be happy and process the problem and solve it. So here what I see is the log from CBC telling me, okay, I'm solving the problem. I can also, set to silence before solving to avoid having CBC printing its whole life and biography before everything. Right. I will skip this part because you can see it by yourself. What time is it? Yeah, 34. I think I will stop here. If you have questions, we have some funnier example on linear regression and semi-definite optimization afterwards, but I prioritize on answering questions first.
Hello.
Yep.
Okay. So hypothetically, if I wanted to spit out that whole process of the verbose solving process, can I export that to a text file instead of just throwing it into the REPL?
So the problem is, so the printing happens on the solver side. This will depend on the solver itself. Some solvers allow you to, instead of logging to println, to printing to the terminal, they allow you to give a file, but that depends on the solver itself.
So there isn't like a general Julia trick for printing what you see in your REPL to a text file.
So there is, so there is a general Linux trick for this. All right. So if you run, well, let's say I'm going to create a script, and this will println hello, and this will be file.gl. So I created this file.gl file that just contains one single line of Julia, so I can run it. Hello. Oh no, file, and this will print me hello. So what I can do, if I run something in the terminal, is I can add some text files here.
You mean you can pipe it?
Yeah, you can pipe it, exactly.
All right.
And so in that case, what I have here in log is the result, hello. So this is what was normally printed. So there, first question in the chat, can we see what the optimized function sends to the solver? So basically what you can do is before passing something to the solver, what you can do is also you can print your model and you can see what is actually passed to the solver. So this is the equivalent model sent to the solver. Right. Second question, is it possible to use high precision solvers with jump using bigfoot coefficient instead of float? Yes. So one good example, so not with jump itself yet. Jump is working on that because, for example, it's only float 64. And the reason is most linear and mixed integer linear solvers, just support float 64. It's hard coded in there. You cannot change it. Also because most of them are like old-fashioned C, C++ bit solvers. But you have some pure Julia solvers that support arbitrary precision types. One of them is Tulip, that I think I mentioned on my last slide. Yeah, this one here. So Tulip supports arbitrary numbers as long as you can do linear algebra on them, and so including big floats. And so this is an interior point solver here. So yeah, Jump doesn't support it. I think, yeah, Convex supports it, like Daniel said. And otherwise, you can use the underlying interface called mat_opt interface to build your problem and then convert it to big float. All right. In the context of SDP, there's an interface. Yes, there's also, I mean, you can also do SDP directly in Jump, and I guess I will just show you quickly a small example. So here, I took this from a paper from 2003. The reason I took an old paper is, so the first time I gave this talk, this was at the University of Edinburgh, and some people were there. All right, so I will try to find the best correlation matrix from data, given that I enforce sparsity. So I enforce some zero on some places in the correlation matrix. So I enforce independence of some variables. So I try to find some matrix C that's as close as possible to the correlation matrix of some data X, subject to my diagonal has to be 1, my matrix has to be semi-definite positive. So this is your SDP constraint here. And some Cij have to be 0. And that's the model here. So first I create my data. So I create some independent variables first, and then I create some 3 columns depending on the first 3 columns to have something with some correlations. So you have some places with higher correlation, like 7.5, 7.4, 7.4, and so on. So I create some data first, and then this is my model. So I create a model called sparse score, and I pass it the SCS optimizer, which supports semi-definite optimization. I'm going to set it to silent to avoid printing its whole life like before. And then I will create my only variable, which will be my matrix of n by n elements in the PSD code, so in the positive semi-definite code. So I create my variable directly with the constraint that it has to be in the positive semi-definite code. And then my constraint, my constraints on the diagonal here is that all the elements on the diagonal have to be 1. And the last constraint is for some ij, I will say that the corresponding element has to be 0. So just ignore this. This is for printing that I want to give a name to my constraint. Otherwise, the key thing is my constraint here is just Cij is equal to 0. And then I set my objective, which is minimizing the error between C and the correlation of X. And I can optimize it. And some people asked in the chat, how do I get the output? So in that case, so the output value for C I get with this jump value function. So you can get the value for a corresponding variable. And since I have multiple variables in C, so this is a matrix, I want to get all of them. I use this dot syntax here. All right. So what's the type of the output? How to call the optimal value? So this is for the optimal value of a variable. If you want the optimal value, let me check where I added this. All right, here, getting results. So here, the first thing to do, if you have, is to ask what's the termination status. For all your optimization problems, you will have an a status. So in this case, I have an optimal solution, which means I found a solution, it's finite, and I stop there. You can ask for a primal status and dual status also, which is very useful for primal dual problems, well, solution processes at least. So in that case, remember, so this was my first problem. I had some binary variables. So I have a feasible point for my primal status, but I have no solution on the dual, because I don't have dual solutions. It's a binary problem. I can also ask for the value of a single variable with jump value of x here, and this is 0. I can ask for the objective value here. So these values will make sense only if I have some actual solution here. So you don't need to have optimal solutions. Sometimes you can have a solution telling you I have slow progress or I finished because of timeout, but I still have a solution. And I can add this dot here for element-wise values. And so here, this was my matrix Z, and I can ask for all the values here. All right. So yeah, that was it for how you query the information out of a problem. So someone asked, but so the actual solver input, the data structures out of the solver API that is passed to the solver API. So the solver API have different interfaces. You can see that in the solver packages. So jump is one package in Julia, well, one Julia package, and then you have solvers that have different packages. So CLP has a package, CBC has a package, and there you can see what they actually expect. And there's a layer. So jump is a modeling interface, and there's a layer below called MatOpt interface, which is for a common data structure for mathematical optimization problems. So if your problem is modeled with MatOpt interface, using MatOpt interface, then you can pass it to all these solvers. Jump is mostly there for the convenience, for the syntax, for making your code look like your model. All right. Yeah, I think I didn't forget any question. Oh yeah, since we didn't see any picture before, so here is the example with a quadratic problem. So for solving regularized linear regression, L2 regularized linear regression here. Oh yeah, and this jumps back a bit also to the point I had before, that here you can do everything in Julia, including reading your data, plotting it, exploring it, creating some algorithms for solving your problem, and then plotting the results afterward. Oh yeah, in that case, so that's a good point. So here for my regression problem, let me check where right here, my model is here. So in that case, I didn't use CSC for the regression problem. I used IPL. Oh no, yeah, you're right. You mean for the SDP example. So the question is, SCS expects linear objectives, and you have a quadratic one. This is correct. So this was, yeah, this example here. So SCS can support semi-definite positive constraints, but it doesn't support quadratic objectives. So how does it work? Well, JUMP will convert if you have a given input problem, and it can be mapped to some form where the solver accepts it, then there's a mechanism in JUMP called bridges that will transform your problem into a form that's accepted by the solver. And so in that case, we have a quadratic objective that's not supported apparently by SCS, sorry. And in that case, what we will do, I think likely, is create a second order cone constraint for the quadratic objective, and then pass this to SCS. So, and this is done because I used a JUMP model, which is, it's meant for convenience. And so it will just try to transform your problem into something that's compatible with the solver. Of course, if you have things like, if I have a quadratic objective or conic constraints that are really not supported, like I do have only a linear solver, it will throw an error saying I cannot convert that. But if you have some things that can be converted, then the JUMP mechanism will adapt your problem to something that's compatible with the solver.
Can I ask a question to that still?
Yeah.
Sometimes this conversion can be done in the element as well, but it may be very slow. So is this fast in JUMP?
Yeah, so the bridge mechanism is extremely usually very fast. What it does is, the transformations are, the constraints are represented as function in set, and functions are special types, and sets are special types. And it will basically look in a graph for transformations from your constraint to anything that's the closest possible to what the solver supports. So the solvers, when you define a solver interface, you basically specify what function constraints do you support. And then JUMP will look for the shortest path from the input problem to the solver supported problem. And if you already know what you're doing, like you know that you have a form compatible, then you can say that you can use what's called a direct model instead of a model. And for this, you need to have all your functions and constraints supported directly by the solver. But yeah, my opinion is also, question, which editor do you recommend? So of course that depends a bit on your background, what you're familiar with. For convenience, I usually use Visual Studio Code or some variants of it, which is, I think, so these days Atom has been more or less discontinued or is just in maintenance mode, so I wouldn't advise it. So Visual Studio Code has a great support for Julia, so you can run Julia live code directly, so within the editor without leaving it or having a REPL on the side. I still use a bit Jupyter Notebooks, which I use actually for creating these slides. There's also an interface called Pluto, written like this. And so this is also a kind of notebook interface, but a bit more friendly, I would say, than Jupyter Notebooks. A bit more foolproof, I'd say, at least. But yeah, for code edition and working on code itself, like writing code, I usually use Visual Studio Code these days. But yeah, otherwise, compared to other languages, I also spend a lot of time directly in the Julia REPL because it has a lot of things already there, like going to package mode and seeing which packages I have installed, looking for help, or I don't have dot, so I need linear algebra, and then I have dot available, things like this, even creating functions on multiple line. If I create a function, and then as long as I don't type an end, it will continue on a new line. I can navigate on multiple, like I do this, and then 2 plus 2, and then I can navigate with my arrows normally, which is quite often not the case in many REPL. So yeah, it's the Julia REPL is really well made for working in there also. So I do spend a lot of time just here messing around, trying ideas and so on. You also have auto completions. Like I created this function f. I can create another method for f that takes x, like we saw before. And now what I can do is I type f and then parentheses and tab, and it will give me all the methods that I can call. So it tells me I have f with empty parentheses like this, and I also have f with 1x. And I can also have a special one that's just with integers, and then it will give me the 3 of them. Like you have f, then you have f for an integer, and then you have f with anything that's x. So you have many tricks in the Julia REPL that make it really convenient to use. Yeah, so the package mode to get in this, this is the square bracket. The square bracket like this. So this switches me to this blue mode here called package mode, which is basically where you interact with your packages. And so here I can do status and see, so what's my environment? I'm in Julia 1.6. And then what are my installed packages here? So I have skip, revise, all these. And then I can add a package. So do I? Yes, I can add. What would I want to add here? So, oh yeah, basically if I start to type something like T and then I tab, it will give me all the packages starting with T that are registered officially with Julia. So I can even see which one to install. Well, I don't think I have data frame. So like I start with data F and then what are the names I have? Oh yeah, data frames. I can need that and then I'm gonna install it. And so it will download it directly from the official registry of Julia. So in that case, it will download it, install it, give me the version. It will keep it compatible with my other packages. Yeah, otherwise again, to get the repo, so everything will be here, the link I also posted in the chat earlier. Yeah, if you want to ask questions, otherwise, yeah, my GitHub and Twitter accounts are also the same one. So yeah, you can just ping me anywhere. Oh yes, Bernard is highlighting there's a shell mode. Yes. So sometimes when I'm in the Julia REPL, just like Bernard said, I don't want to quit Julia just to do some shell commands. Like Guillaume showed you earlier ls. Like, oh, I don't remember which files I have now. And so what I can do is type semicolon like this one, on the first thing on my line, and this will shift to shell mode. And shell mode is just like being in your normal terminal. And so this means I now have ls, for example, for seeing which files I have here. I can touch to create a file, and so on. So I can really stay in the Julia REPL and just run my normal shell commands also.
Any other questions for Mathieu?
How do I get back from the shell mode?
Oh yeah. So this is the same for package mode, shell mode, and help. So if I switch to a mode, I can just do backspace, so like erasing a character. And this will get me back to the normal Julia mode. So the Julia mode is the default. Then so this will do package mode, this will do question, and this will do shell mode. And then backspace gets me back to the normal one.
Hello, I'm Marcus. May I ask you if you type in a method or a function, and is it when compiled actually? If you type that, for example, in a Jupyter notebook, or?
So yeah, that's a good question. So it will not. So the trick is it will not be typed when you create it. Like if I create, well, I created 1,000 f functions. So let's create a G one for once, x and y, and it will be x over y. So I created a new function here. It's not yet compiled. What it did is just create it. And the moment it compiles it is when I call it, actually. Oops. Yeah, of course. So this compiled my function. And my function is now compiled. And so the trick is if I call this, it might not work because Julia got a bit faster on compilation. But so if I time it, okay, no, this is way too fast. I can't even measure time on that. But basically what happens on some functions is, so this time macro will measure the time spent to run this. And so the first time I run a function with a given type input, it will compile the function specifically for these types. So it will compile a specialized method, like to native code. And so the first time it takes a bit more time because it does the compilation. And then all the other times afterwards, it's faster. It's the same thing for plots. The first time you plot something, it will compile the plot function. And so it takes a bit of time and then it's faster.
Thank you.
And yeah, one trick for this, if you really are into low-level code, what you can do is use these code macros, and you have different ones, and you can see the code that's compiled at different levels. So you have like the code lowered, which is still Julia code, but a bit transformed. And you can go all the way to what's called code native, which will show you basically the assembly code for your function, like you would get if you were compiling some C code with GCC. So if I do code native for my function G with 3 and 2, it will show me the assembly corresponding to adding two numbers together. Oh no, dividing two numbers, sorry. So here I just have these two instructions. Yeah, I'm not even sure what they are doing. And then this is the division.
Okay. Has anyone more questions?
May I ask another technical question? Are the arguments given by value or references in this function?
So in this one, so for native types, this would be by value. If you create a trick I had is, so I presented structs here for creating structures. And if these are structures with just a bit field, so with just, for example, an integer and a float, then this can also be passed by value, because basically everything is transparent. And the trick for that is that creating a structure is immutable, meaning you cannot change v and f afterwards. And so basically you can pass it by value or reference because you cannot change it, and this would be equivalent. Now, if you create a mutable structure, or if you have anything that could be changed, then this would be passed by reference, because you cannot guarantee that it will be equivalent to pass A or a copy that's modified of A. But yeah, so for example, if you pass an array, like I pass to my function this array, this will be passed by reference always. This will not copy the arrays.
So you can do inline internal modification.
Yeah, exactly. Yeah.
On the argument.
And the convention for that is, for example, so we showed a function with a bank here, and this is the convention in several Lisp dialects in Ruby too, that when you have a function that modifies its argument, it will take a bank. Like I will first create v that will be a vector with 1 and 2, and then I will use push to add to v 11. And now my v vector contains the 3 elements here.
Thank you.
A question I always thought about. I have a beautiful code written in MATLAB. Do I have to write it from scratch in Julia?
So you can call MATLAB code from Julia. So there's a package for this, but I would say that, I mean, depending on the size of the code and what it calls, the syntax will be extremely close. I mean, you saw the broadcast syntax is roughly the same for element-wise operations and so on. Transferring code from MATLAB to Julia, I think, might be the easiest transfer to do compared to others. I mean, transferring some Fortran handcrafted code that's been worked on for 40 years is something else, but MATLAB code should be doable. Oh yeah, someone posted the matlab.jl package. And similarly, someone asked, can we call R in Julia? Yes. So you can call R in Julia, and you can call Julia in R also. So the two ways work, and the same thing for Python.
And you can call C also.
Yeah.
Yeah.
So you have, so I won't go into the details here, but you have a function called ccall, which is basically called in my shared library, this function with, and so you have to give the types in that case of the function, and it will call your function in the shared library. So you can call C, and this is a zero cost foreign function interface. Yeah, calling C and Fortran code is done in the same manner. And so basically all the solvers, all the optimization solvers written in C, in C++ are called in this way. And so this is fairly straightforward. I mean, of course, this is still calling C, so this is straightforward as it would be to call C from other languages, like from C itself.
May I ask another question? So what do you recommend for symbolic computation? What are the best packages?
So yeah, I mentioned in the demo Sim engine, which is fairly actively developed. There's a wrapper for SymPy also, and SymPy has been developed for quite some years now. It's fairly established and works well. And since a couple a couple of weeks ago, there's a new Julia open source organization for symbolic computation. I think Julia Symbolics. That's basically been born from some equation or expression handler in the differential equations ecosystem. So there's a new package that was basically here but hidden in another package for symbolic computations. So they decided to create a new one for that. I'll try to symbolics. Yeah, I'll try to find it and post it in the chat on the side. But yeah, you do. So you do have several ones. I would say SimEngine and SymPy work well. SimEngine is definitely faster. And then this will depend on your needs, I think. But yeah, SimEngine does work really well.
Thank you.
Oh yeah, I just posted in the chat the Julia org that was created, so Julia Symbolics. But yeah, this is still fairly recent, so they're starting to work now on getting a proper symbolic package in complement of the other ones that already exist.
Okay, maybe a last question before we go to lunch.
How is it with updating all these packages? If the author updates them, do I have to, well, how do I recognize it?
Mm-hmm. So there are two parts. So the authors so register the package the first time, and then they register new versions of the package. So it doesn't get updated every time you push a commit, for example. So authors decide to release a new version, like a new minor or patch version of a package, and then so once you have a new version, basically, if I do up or update, Julia will check in the repository for the packages I've installed here and their dependencies. So all the so these are the ones I installed, but they depend on packages themselves, and so I have more packages installed than that. So in that case, I do update, and it will check on the official Julia registry which packages do I have that should be updated. And then, for example, if I have a new version, it can happen that, oh yeah, here, for example, I depended before on qt.jl, and I don't anymore because my new versions don't depend on it. In that case, it will clean it up and remove it from my dependencies because I didn't install it. It's some packages that I installed that needed that package, and I don't need that anymore. And so for all the others, yeah, for all the other ones, it basically upgraded everything from one version to the other. So yeah, and another thing I didn't talk about here because we didn't have much time was there's a way to isolate your environment. So in that case, I'm in my global Julia environment, but you can create local environments for given projects. Say, for example, here I depend on jump 021, but I want to create a new project on jump 020, and I don't want to mess up the rest of my environment. And so for that, I can create a specific environment, and in that environment have jump 020 and some other dependencies. Well, I can show you an example actually. One example would be the slides for this workshop here, so the repo. If I open it here, I can check what do I have installed. And so in that case, I have some things installed that I don't have globally, like SimEngine or Unitfold. And I don't have this installed on my global Julia installation because I rarely use them. And so this is a bit like virtual env in Python, for example, where you can create for a given project specific dependencies, and so you don't have conflicts with your other dependencies.